Hi all, this is Mr. Yeager for Physical Science. Today we are looking at the gas laws. Now I want to kind of give you a heads up with this for physical science. The gas laws, we are only looking at them in terms of, as this says, the relationship between volume, temperature, and pressure. Looking how that manipulates those measurements with gases. We do not get into the actual formulas with Boyles Law, Charles' Law, and Gay-Lussac's Law. Sorry if I say that wrong. I don't know how to say it. I'm going to say it that way. So we will talk about each of those laws, but it'll only be this inverse relationship, direct relationship talk. No formulas involved. All right. So when we're looking at gases, all right, we're going to be looking at these three variables: volume, temperature, and pressure. Because again, as we talked about in the state of matter unit, gases are spread out everywhere, and these are three quantities that can affect what a gas is doing officially. Basically, the space it's taking up, how quickly it's moving, etc. So here we go. So first off, let's go over the terminology, volume and temperature. These are two terms that we have used already quite a bit in class. Volume is the amount of space an object takes up, how much it spreads out, all right, measured in liters. Temperature is, again, the average kinetic energy of the particles, all right. That is, again, not referring just to how hot or cold something is, but again, how quickly the particles are moving, how quickly they are able to move through space. And again, in physical science, in any science course, temperature is measured in degrees Celsius or Kelvin. All right. So those two things we kind of already know. Gas pressure, though, is one that we really haven't talked about too much yet. Gas pressure is caused when the gas actually hits the sides of the container. Okay. So again, this is your good diagram of what a gas looks like, okay? In a container from a molecular level, they're all spread out. They're zooming away from each other, moving very, very quickly. And what happens is when they hit the side of the container, since they're matter, they create a force or pressure on that particular side. Again, force and pressure are not the same thing, all right? Pressure is force over an area, but it creates that force over that area and therefore pushes on the container. It's what happens when you blow air into a balloon. Basically what happens is you're blowing in millions and millions and millions, quadrillions. I mean, I can't even talk hexillions. I can't get the correct prefix for it, of these air particles, and they're all pushing against the sides of that balloon, all right, causing that pressure very quickly. As this says, more particles that hit the sides, the greater the pressure. The unit for pressure is called the atmospheres, okay, or atmospheres. You might also see later on something called a Pascal, or you could see millimeters of mercury. Those are all the different units for pressure, the standard units, all right? Again, though, we're not actually calculating anything, but you might see, hey, you have 5 atmospheres, then it goes down to 3 atmospheres. That just is telling you that the pressure is decreasing. So, what do we do with these? We have 3 laws that basically combines 2 of the variables, all right? So in each of these laws, 2 variables are being manipulated. Again, our 3 variables are volume, pressure, and temperature. In each law, 2 are going to change, 1's going to stay the same, all right? Because they all end up affecting each other, so we have to keep one constant to see how the other 2 affect each other. So our first one is Boyles Law. Boyles Law, okay? It relates volume and pressure. And so that means temperature has to stay constant. Temperature has to stay the same. So if we think about what happens here, if I manipulate pressure and volume, all right? Again, what I can look at is basically if I apply more pressure to a balloon, if I start squeezing a balloon, apply more pressure, what happens? Basically, I'm going to decrease the volume. If I push things more closer together, I can decrease the volume. But what happens, okay, again with the pressure, what I'm saying is I'm increasing the pressure, decreasing the volume. Down here in our diagrams, you can see if I increase the pressure or decrease the volume, I increase the pressure. So what does that mean? pressure and volume are inversely related. As I increase one, the other goes down. If I push more, I make things tighter. All right? I mean, anything that you can get the idea that, you know, if I keep on packing more and more students in my classroom, there's going to be less and less room. I'm decreasing the volume that you guys basically have, and you're going to feel more pressure of other people possibly pushing up against you. All right? If you've ever been in a very crowded area, you've decreased that volume, increased the pressure in that area. Okay? So that's what we're basically looking at. If I have to look at it from a graphical perspective, so we will look at it from graphs. If we remember, any inverse relationship is basically, if you have a graph, is a line going down. Okay, a line sloping down. We want a downward sloping line. It doesn't have to necessarily be a curve, okay, but a downward sloping line. We keep it pretty simple in this class, all right? If it's a curve going down, yay, okay? But it's a downward sloping line in this situation, okay? As the pressure increases, the volume is decreasing. That's what we have here. Same thing goes if it was pressure versus volume, we would still have that downward approach, okay? That downward line. Inverse relationship between the two. Our second law is Charles' law. In Charles' law, I'm going to relate volume and temperature, so pressure staying the same, okay? Volume and temperature are being manipulated. I think most of you guys can know this. If you've ever put like a can of something over a fire, if you increase the temperature, what happens? Actually, that's a bad example, sorry. Let's do a different one. The best one's probably the hot air balloon. Sorry, I already jumped it to the temperature and pressure. A hot air balloon. Okay? If you with a hot air balloon, we add heat to that hot air balloon. Okay, this is my bad picture of the fire. That's a terrible picture. Let's try that again. Let's do that, and then here's the fire. That's still a terrible picture. All right, whatever. So what we have is with the hot air balloon, what happens is if I add heat to the hot air balloon, what does it do? It expands. Anything I add heat to, it expands. All right, is what we're looking at. You can even think about that with even metals, bridges, and things like that. The objects expand when they get hotter and hotter and hotter. Okay? Vice versa, if I decrease the temperature, I'll decrease the volume. Okay? If you put something in the fridge, it's going to shrink. All right? If you've ever put like a plastic bag with something that you accidentally didn't get all the air out and you put it in the fridge, all that air will compress. Okay? It'll get, not compressed, but just decrease in space. There won't be as much pressure anymore. Okay? With the temperature and volume, all right, they are obviously directly related in that particular case. All right? Obviously, we can see that pressure is going to have an issue too, but we're going to try to keep that the same as much as possible. So even if the pressure does change, this would also still work the same way. Okay? So if I put this on a graph, since I see a direct relationship, I should see a straight line going up. Okay? So not straight, but like a sloped line going up. So Charles' law is showing you volume and temperature directly related. The last law that we have is this Gay-Lussac's law. It relates pressure and temperature, constant volume. So now we've gone through the whole cyclical piece of everything. So in this case, if I increase the pressure, I increase the temperature. It's probably easier to understand this as, come on thing. I guess it doesn't want to do it. There we go. If I increase the temperature, let's go from it that way, I'll increase the pressure. So that's what I was trying to show beforehand, or say beforehand. If you ever put like something with a can and a sealed can on a fire, what's eventually going to happen? It'll explode. Okay? So obviously with an increased temperature, there's more pressure inside of it. If it can't contain it anymore, you can cause an explosion that way. Okay? So that would be your example of Gay-Lussac's. Again, direct relationship between the two. All right? So on a graph, this will also be a straight line going up. Okay, a slope line going up. So Gay-Lussac's and Charles are direct relationships. Boyles is inversely related. And that is basically it. All right, thanks.